Hello to all participants of the conference, and thank you to those of you who joined us in this special session on smart electrodes. Our team from several universities in Europe are presenting their research on the application of electrochemical techniques in designing functional devices. My name is Ramunas Levinas. I am a late-stage PhD student in Vilnius University, Lithuania, and my presentation will be on the application of electrodeposited molybdenum disulfide films for hydrogen evolution reaction catalysis in acidic media. To give you a short outline of the presentation, first I'll discuss some of the benefits and unique or interesting properties of molybdenum disulfide materials. Then we'll move on to the experimental part, where I'll explain how we electrodeposit and characterize the films and electrodes. Finally, and arguably this is the most important part, is characterization of the hydrogen evolution reaction electrocatalytical properties. We use methods you may be familiar with, like Toefl analysis, but also more advanced techniques like electrochemical impedance spectroscopy, the benefits of which will be shown later. So why is molybdenum disulfide interesting? Well, as is pictured in this figure, molybdenum disulfide can be shaped into various unique morphologies, or, as in our case, it can be deposited on substrates with unique structures and morphologies. It has been shown to be a highly active hydrogen evolution reaction catalyst with a free hydrogen adsorption energy of around 0.08 electron volts, and here the closer to zero, the better. As is important for catalysts, it is precious metal free and therefore relatively inexpensive to produce. Many different synthesis methods exist, although as electrochemists, we are mostly focused on electrochemical deposition. About its stability, molybdenum disulfide is fairly electrochemically and chemically stable, although it is susceptible to oxidation of active sites in air. And another interesting property is its band gap, which is around 1.23 electron volts, so the material does have potential as a photocatalyst. Now we move on to how we obtain the molybdenum disulfide films. Firstly, we use cyclic voltammetry to examine the working potential range of the system. The electrolyte had 25 millimoles of ammonium tetrathiomolybdate, which is the precursor for molybdenum disulfide. CV scans were taken on a copper wire with a surface area of 1 square centimeter, as well as a 3D copper foam electrode, the surface area of which is unknown due to its complex structure. The actual substrate electrodes used are pictured below to the left and to the right. And here I must point out that the wire electrode is only presented for comparison, and all of the subsequent experiments were carried out on copper foam electrodes. So from the actual CV scans, it is first of all apparent that the magnitude of the current is much larger for the foam electrode, which is obviously related to its larger surface area. Several peaks can be seen in the curves. The sharp increase in anodic current is likely related to corrosion of the copper substrate or oxidation of electrodeposited molybdenum disulfide. A small anodic hump at around minus 0.8 volts may be related to desorption of hydrogen. And finally, the cathodic current from minus 0.9 volts and onwards is decided by two processes. That is, the reduction of tetrathiomolybdate to molybdenum disulfide and simultaneous hydrogen evolution. In this slide, you can see the scanning electron microscopy images of the surface morphology of molybdenum disulfide films electrodeposited on a copper foam electrode. Now, the ligaments on this particular foam are about 200 micrometers in diameter, so it is a large foam. Upon closer magnification, we see that the surface morphology is rough and that the molybdenum disulfide does not cover the substrate homogeneously. There are pores, or rather empty gaps in the surface where molybdenum disulfide growth had not occurred. As well as that, there are nodules that protrude from the surface, and the film overall cannot be said to be flat. EDX, that is energy dispersive X-ray spectroscopy, was used to analyze the atomic composition of the deposited films. We found molybdenum, sulfur, as well as oxygen in the material. Molybdenum and sulfur ratio suggests that the material exists in a non-stoichiometric sulfur deficient state. This is in line with scientific literature, where it is well established that Electrodeposited molybdenum disulfide is amorphous and sulfur deficient. To characterize the hydrogen evolution reaction catalytic activity, we performed linear sweep voltammetry scans in acidic media, 0.5 molar sulfuric acid. The electrodes were prepared galvanostatically by carrying out the deposition for an increased amount of time, which relates to increased charge. The legend on the graph shows the charge in coulombs, and immediately it can be seen that increased deposition charge correlates to better hydrogen evolution reaction catalytic activity. That means that the same current is reached at a lower overpotential. Because more material is deposited, this can be assumed to relate to increased catalyst loading. The Toefl slope is also a useful parameter in characterizing and comparing hydrogen evolution reaction catalysts. It is obtained by plotting the logarithm of the current against overpotential and finding a linear trend. This is presented in the graph on the right. Lower values correspond to better activity. Molybdenum disulfide materials often have slopes in the 40 to 50 millivolts per decade range, which is true in our case as well. Whether or not a catalyst is electrochemically stable is an important thing to consider. Different experiments can be used to test stability. Here we used a galvanostatic step technique where an increasingly cathodic current is applied for steps of 500 seconds. The same electrolyte was used. From these curves, we see that the films are fairly stable at low applied currents. For example, at minus 20 milliamps, the overpotential trend is fairly flat. However, at larger applied currents, for example, minus 50 milliamps, a drop in overpotential becomes apparent. If it takes a larger overpotential to reach the same current, we conclude that the film is losing activity. The reasons for this are likely related to breakage of chemical bonds in the structure of the molybdenum disulfide film, as well as possible mechanical destruction by vigorous hydrogen bubbling. And finally, I would like to discuss the use of electrochemical impedance spectroscopy and show you what information it can give us on heterogeneous catalysts. This method is especially useful for heterogeneous catalysts because it only probes the catalyst solution interface and not the bulk material. To put it simply, the way it works is that the system under investigation is perturbed by a potential that is modulated at a certain frequency. This induces a current response. This current is registered and mathematically transformed into an impedance spectrum. Impedance measurements are typically performed potentiostatically. So for our system, we chose overpotentials over the entire experimental range, from minus 0.1 to minus 0.3 volts, to encompass all possible kinetics of hydrogen evolution. The impedance spectra that we obtained are presented in this figure on the left. Now, at the very least, it is worth comparing them by magnitude. Essentially, the smaller the spectra, the smaller the impedance. For example, the impedance of the system at minus 0.1 volts is much larger than the impedance of the system at minus 0.2 volts. This can also be inferred from Bode coordinates, which are shown in the inset, where the y-axis is precisely the total impedance of the system. If we recall the polarization curves, the hydrogen evolution reaction current at minus 0.1 volts is next to zero, but at minus 0.2 volts, it's around 40 milliamps. Therefore, there are different kinetical data in these spectra. What we then do is apply equivalent electrochemical circuit fitting, by which we draw an electrical circuit with components that correspond to physical parameters in the system. In the circuit shown here, the most important parameters are the double layer capacitance, charge transfer resistance, and the component related to pseudocapacitance, which is caused by hydrogen adsorption and desorption. We then use computer software to fit the spectra to a mathematical model and then calculate the values of all the parameters seen in the equivalent circuit. And these parameters represent the electrochemical system's physical parameters. For example, the double layer capacitance is proportional to the electrochemically active surface area. So even though we don't know the actual surface area of the foam substrate, we can at least operate with values that are proportional to it. The charge transfer resistance is also important, as it is proportional to the rate of electrochemical reaction, in this case, the Hairovsky hydrogen recombination step. And the inverse of the charge resistance as a function of overpotential gives us information similar to polarization curves. To summarize, we have electrodeposited molybdenum disulfide films onto copper foam substrates and use them as efficient hydrogen evolution reaction catalysts in acidic media. The electrodes are active and stable, but their Toefl slopes are larger than ideal. And finally, we used electrochemical impedance spectroscopy to examine the kinetics of the hydrogen evolution reaction and found that the overall activity of these electrodes is determined by the hydrogen absorption step. So thank you all for your attention. Here I would also like to acknowledge funding from the European Union Horizon 2020 project Smart Electrodes, as I have mentioned in the beginning of the presentation. And again, thank you all for your attention.